Okay, so we've been looking at the area between the curve and the x-axis, and I suppose kind of referring to that nearly as area under the curve, which I suppose it is down as far as the axis there, and we're only ever really calculating, or I suppose integration really only calculates for us that particular area, so under the curve down to the axis, and it doesn't go any lower than that. So we were looking at maybe with respect to the x-axis, and that would be dx, and I suppose realistically that's what a lot of the integrals we've been doing have been. They've all kind of been dx. Now we obviously could also be given a function like the one here and asked to calculate or compute that area to the y-axis. Okay, and I suppose there are maybe multiple ways that you could look at this and calculating this area. This specific example here, it definitely would seem a lot easier if we could do it from the curve to the y-axis between those y values. It seems like that would just make the whole calculation an awful lot easier. And the main thing to notice really with that would mean that I need to integrate with respect to y, because my bounds would be y values, so therefore my integral needs to be dy. So it would be slightly different to the integrals we've been looking at already. So the steps I've laid out here, fairly straightforward. The first step is write the function in terms of y, so just rearranging the function, kind of expressing the function instead of in terms of x, expressing it in terms of y, and then integrating with respect to y using the bounds on the y values. Okay, so looking at the example here again, we can see that the function, or the area I'm trying to find, is between y equals 4 and y equals 9. So if I could integrate with respect to those bounds, that would make my calculation an awful lot easier than trying to sort this out with respect to the x values. So finding the area here, we need to rearrange our function. So our function currently is y equals x squared. If I want to rearrange that function, I would do square root of y equals x, and then to make it easier to integrate, I would probably express that as y equals a half. So the function here has been re-expressed now as x equals y to the power of a half. And all that that really means is our usual functions give us a y value for the x values that we supply it with, whereas this function now, with the way it's been expressed, is more giving us x values for the given y values. Okay, and I suppose the idea of having the square root here does open up other potential avenues and does kind of change the expression of things here. And I suppose this is why we're looking at it specifically in the first quadrant, because as we allow ourselves into other quadrants, then we have that if I select one input, I can get two possible outputs. So think about 9 here, for example. Square root of 9 should be plus or minus 3, and then we get into kind of a larger discussion of, is this considered a function and all of this. So that kind of, I suppose, restriction of the first quadrant maybe just allows us to still have that understanding of a function. I'm only really looking for those values in that kind of range here. Anyway, all of this to say, we're going to integrate the function y to the power of a half dy. So making a little note here. So with respect to y, as opposed to with respect to x, between the values of 4 and 9. So that's going to be y to the power of 3 over 2, so raise the power by 1, divide by the new power, and evaluate at 4 and 9. So that is 2y to the power of 3 over 2 over 3 evaluated at 4 and 9. I know I'm only looking for answers in the first quadrant, so that's going to, I suppose, impact my overall results here. Okay, so let's evaluate some of these values for ourselves. And okay, so let's evaluate these. So 2 times 9 to the power of 3 over 2 all over 3 is 18, minus 2 times 4, 16 over 3. So 18 minus 16 over 3 gives me 38 over 3, which is approximately 12.66 or 67 units squared. Okay, so very, very similar in approach. Very, very similar in approach. but just that idea of rearranging the function, expressing it in terms of y as opposed to leaving it in terms of x as we have seen. Okay. So let's look at one more such example then. So the function here is x cubed, and again we're looking to calculate the shaded area, very similar really to the example we have there. We're looking for the shaded area between this curve and the y-axis from y equals 0 to y equals 8. So I suppose if you're kind of looking and saying, well, how on earth am I going to know if they want me to do it with respect to x or y, it really is as simple as just looking at the values that you're given. If you're given bounds in terms of y, then that's what you're integrating with respect to. So the first thing, again, as we did in the last one, is just going to be to rearrange my function, because currently the kind of the kind of variable that I'm working with really is x. This is in terms of x, or with respect to x here, and then y kind of being the dependent variable, whereas we want to kind of change it the other way. So that's going to mean x is y to the power of a third. So using that kind of radical or rational idea as opposed to the kind of cubed root idea here. So I want to integrate y to the power of a third from 0 to 8 dy. So that's going to be y to the power of 4 over 3 divided by 4 over 3, which gives me 3y to the power of 4 over 3 over 4 to be evaluated at 0 and 8. So that's 8 to the power of 4 over 3 divided by 3 minus 3 to the power of 0, or not 3 to the power of 0, but 3 over 0. Sorry, excuse me, that should be over 4 as opposed to 3 here. Okay, so working with the 8 first of all. 8 power of 4 over 3 divided by 4 gives me 12. Looking at the 0, I'm expecting 0. We're multiplying something by 0. We get an answer of 0. So the overall answer here is 12 units squared, square units, however you want to express that idea, but just having that idea of units squared. Square units, perfect as well. Doesn't matter. Okay, so the area there given 12 units squared. Really the only difference that we're kind of coming up with here is that kind of distinction between integrating with respect to x and integrating with respect to y, which is a good thing to look at generally anyway, and then applying that to area, just making sure that we look at the bounds that we've been given, and then ensure that what we're integrating is integrating with respect to those bounds. Okay, that's really the key thing that's coming out of this here. So the only last little thing to look at then, the video to continue into now, is curves going above and below the axis. So that's going to be the next little thing to be looked at.